Hi there, my name is Miss Townsend and I love math. Welcome to Math with Townsend. This video is for grade 12 students in advanced functions in the trigonometry part of the course. In this video, we're going to look at the shape of the reciprocal functions and also the shape of the tan function. So again, in this video, we're going to look at the functions y equals tan x and the three reciprocal functions cosecant x, secant x, and cotangent x. And the way that we're going to examine and explore the shape of those periodic functions is by using our knowledge of the other trig functions, y equals sine x and y equals cos x. And by using these functions and our understanding of them, we're going to develop these four graphs. And let's start with tan x. So again, we want to create a picture of what y equals tan x looks like, untransformed, and we're going to use our understanding of both sine x and cosine x in order to do that. So the missing piece of the puzzle is the identity that we learned in grade 11, which is that tan x is equal to sine x divided by cosine x. So everything about tan x can be calculated if you know what sine x and cosine x are. So let's start by looking at the 5 key points in one period of sine and cosine. So 0, pi over 2, pi, 3 pi over 2, and 2 pi. And let's see what happens if we use sine and cosine in this formula to calculate tan. So first, at x equals 0, sine is 0 and cosine is 1. So 0 divided by 1, well, that would be a 0. If I move on to pi over 2, the next important value on this graph, now I have 1 divided by 0. Well, we can't divide by 0. That's not a value, and dividing by 0 means that we actually have an asymptote at pi over 2. If I tried to do tan pi over 2, it's an error. It's impossible to calculate tan of pi over 2. If we keep going over to pi, so at pi we have 0 divided by negative 1. 0 divided by negative 1 is, well, obviously 0. And then as we keep going, 3 pi over 2, now I have negative 1 divided by 0. Again, can't divide by 0, so that's an asymptote. And then at 2 pi, so I have 0 divided by 1, so that's a value of 0. So this is all I have so far for the graph of tan, and it's not very interesting yet. I don't know what to do. I have a dot, an asymptote, a dot, an asymptote, and a dot. So now to fill in the rest of the blanks, we're going to use some of the skills that we learned about dealing with asymptotes from the reciprocal function unit. So for example, let's look at what happens just to the left of pi over 2. So right here, just to the left of pi over 2. On the sine graph, we have a value of pretty close to 1. Let's just say 0.99, whatever. And here, just to the left of that asymptote, we have a value that's pretty close to 0. Let's say 0.01. So at just to the left of this asymptote, I have 0.99 divided by 0.01 using this formula. Well, that's a large positive number. And the closer this gets to 0, so in other words, the closer I actually get to that asymptote location, then the bigger that my fraction sine x over cosine x is going to become. Both the values are positive because that's a positive value here, and this is still a positive value. It hasn't yet dipped below the 0 line. And so therefore, I have a positive divided by a positive. My answer will be positive. And because the denominator is getting closer and closer and closer to 0, that means we're going to have an asymptotic explosion in a positive direction. And so it looks like this. So let's continue that logic. Oops, I'm erasing some of my blues, but we'll figure that out later. So now let's move to just the other side of that asymptote. So let me replace my graph here. If we move just to the other side of pi over 2, let's examine what's happening just the other side of that asymptote. So here again, I have a value of positive almost 1. So you can imagine it's something like 0.99. Here, on this cosine graph, you have a value really close to 0 again, but now it's negative because now we've dipped below that center axis. So now I have a positive divided by a negative. So my result, when I do positive divided by negative, my result will be negative. And we have this asymptotic explosion because the denominator is getting smaller and smaller and smaller. And so it's going to look like this, asymptotic explosion in the negative direction. And then if we now say, okay, well, let's move to the next asymptote, which is at 3 pi over 2, and try to apply the same logic. Just before this asymptote, on the sine graph, I have a negative value that's really close to 1, so maybe negative 0.99. And here we have a negative value on the cosine graph, but again, really close to 0. So now I'm doing a negative divided by a negative, so I know my answer is positive, and we have this approaching 0 in the denominator, so an asymptotic explosion in the positive direction. So this ends up looking like this, and if we continued that logic, we would see this shape. So that's what the graph of tan x looks like, you know, a sketch, and that's between 0 and 2 pi. So the actual period of this function is actually pi, but we can still sketch the 2 pi version, and it doesn't change any of the math that we're doing in this course. So again, that's what tan x looks like, and that's how we developed it. So let me just show you a slightly better picture. This is what a computer would do if you said graph y equals tan x. So you can see that we always have this constant sort of negative to positive kind of swoop shape, and it's between two asymptotes that are always exactly pi units apart, and that we have asymptotes every pi over 2. And again, starting at pi over 2 and then pi units apart, that's where every asymptote is. And we'll actually talk a little bit more about how to define that, but just since I brought it up, if I wanted to know the locations of asymptotes, this is what I would write. I would say the asymptotes are at x equals pi over 2, because that's the first one, here at pi over 2. And then every asymptote after that is pi units away. So if I went 2 whole pi units to the left, I would find an asymptote. If I were to go 6 pi units to the right, I would find an asymptote. So the way we represent that is like this, where we introduce k meaning some sort of constant value, and here I'm defining it messily. Let me fix that. Here I'm defining that k has to be an integer, so k is an element of the integer set. And if you multiply pi by any integer, like 6 or negative 10 or 0, and start at pi over 2, so that's what this says, start at pi over 2, and then move this many units away, you'll find an asymptote. And again, that's because the asymptotes are separated by pi units. So if you moved a whole distance of pi, or 6 whole distance of pi, or negative 10 whole distance of pi, you'll find an asymptote. And again, this is significant for writing the domain and range of a tan functions, and we'll get into that in the next video. Anyway, that's what tan looks like. Boop, boop. And let me just clear it up a little bit, make it pretty again. And then for our purposes, this tends to be what's in our head. So our sketch version looks like this. It's not nearly as nice and, you know, fluid and whatever, but again, if we wanted a perfect graph, we would use technology. This is good enough for paper. So that's tan. And now let's look at the reciprocal of tan. So y equals cotangent x, and see if we can develop that equation. Sorry, that function. And again, it's very similar to how we developed the other one, except for because cotangent is the reciprocal of tan, then I can say that cotangent is cosine x over sine x, because all I did was flip that other fraction over. So we're going to look again at the graphs of cosine x and sine x, but using cosine for the numerator and sine for the denominator, we're going to develop the graph of cotangent x. So here, again, are our functions. Here's cosine, it's the numerator, that's why I moved it to the top, and sine is the denominator. So we'll look first at the big 5 point, 0, pi over 2, pi, 3 pi over 2, and 2 pi. At 0, cosine is 1, and sine is 0. Well, 1 divided by 0 is impossible, so there's actually an asymptote at 0. So cotangent 0 is undefined. And then we'll move over to pi over 2. So here I have 0 divided by 1, that's a 0 point. And then I have 1 divided by 0, so that's an asymptote. And then I have 0 divided by negative 1, 0. And then 1 divided by 0, that's an asymptote. So sort of like what we just saw with tan, we now have asymptotes and dots. And let's fill in the blanks. And we'll go a little more quickly, but again, the same idea. We're going to go just to the right of that first asymptote. So on the cosine graph, I'm looking here and a value of about +1, not quite. And just to the right of the asymptote on sine is a positive, but really close to 0 value. So just to the right of this first asymptote, I have a positive divided by a positive. So I know my answer is positive. And we have this asymptotic situation because of the denominator. So here I have a positive asymptote explosion. And then if we look at the next asymptote at pi, just before pi, what's going to happen? Just before pi on cosine, I have a negative value, about -0.99. On the sine equation, I have a positive value and really close to 0. So now I'm doing a negative divided by a positive, so I know my answer is negative. And again, we have this asymptotic situation. So now we have a negative explosion. So this is what's going to happen. And it's going to repeat that same idea here. So you can see it sort of looks like tan. Obviously, the asymptotes have been phase shifted, and also the curve itself is upside down compared to tan. Remember, tan went from bottom to top, and cotangent goes from top to bottom. So that is what the graph of cotangent looks like. Here it is drawn by a computer, so it looks all pretty. So you can see the asymptote at 0, the asymptote at pi, and the asymptote at 2 pi. And where are those asymptotes? So again, just because it's good practice, the first asymptote is at 0, and every asymptote after that is exactly pi units away. So to find another asymptote, I need to move by a whole unit of pi, which is why k has to be an integer. So you move by a whole unit of pi. This is where the asymptotes are for cotangent. Normally I wouldn't write 0 plus, but I just wanted to make sure that all the pieces were there mentally. So again, there's the lovely graph of cotangent, and here it is in our sort of pen and paper example that we would do on a test. So there's tan and cotan. And now let's look at what the other two trig graphs look like. Cosecant. So what do we know about cosecant? Well, we know that cosecant is the reciprocal of sine. So all I need to do is look at the graph of sine x and use some of my reciprocal concepts from earlier courses. So here's our graph of sine x. So let's look first of all at the big 5 points, 1, 2, 3, 4, 5. So first we have 0. 1 over 0, oh, that's impossible. So we have an asymptote. Can't do 1 over 0. Then we have 1 over 1, so the value is 1, okay? So now I'm going to put 1 here, and you'll see why in a second. So I'm going to call this 1, and then so down here I'm going to put -1. So imagine that there's this other line here, just for these purposes. You'll see why, trust me. We're going to put that at 1. Again, we had 0 for sine, 1 divided by 0 was an asymptote. 1 over 1 is 1, so there's my 1 point. 0, so there's another 1 divided by 0 asymptote. -1, so 1 over -1 is -1. And then 0, 1 divided by 0 is an asymptote. So again, just like what happened on the tan and cotan, asymptote dot, asymptote dot, asymptote. Okay. So let's look at what's going to happen near the asymptotes. And remember, it's going to be 1 divided by whatever's happening on sine. So just to the right of that first asymptote, here, I have a positive value very close to 0. So 1 divided by a very small positive number is going to be positive, but an asymptotal explosion. So it's going to look like this. And then if we go to the right of, then we look to the next asymptote. So the next asymptote is at pi. Just before that asymptote, sine is positive and very small. So if I do 1 over that, I get very big and positive. So in fact, we have this. And then if I keep going, on the other side of that asymptote, I now have a negative very small number for sine. So 1 over that would be a negative very big number. And then same logic over here. So this graph is definitely a little tougher to make, but hopefully you can see why I put these middle lines in so that there's a bit more to it. But basically, if you can imagine, I'll do it in yellow. If you can imagine sine would normally kind of fit like this, then it's almost like cosecant has sort of turned it inside out in a dimensional way. I don't know. I'm not trying to say anything mathematical, just get you to kind of see the connection between what happened with sine and what's happening with cosecant. And let's look at that properly. So here's what a computer would do if you said graph cosecant. Looks a little nicer than mine. Where are the asymptotes? Let's write it out. The asymptotes, the first one is at 0, and after that, the asymptotes are exactly pi units apart. So every pi units, we will find an asymptote. So again, the k value is defined as an integer so that I can go 2 whole pi units, hey, an asymptote. 3 whole pi units back, hey, an asymptote, and so on. That's where the asymptotes are. And again, let me clean it up. That's the pretty picture that a computer would make, and this is good enough for our hand-drawn diagrams for pen and paper testing. And then finally, let's look at the graph of secant x. So we know that secant is the reciprocal of cosine, so we're just going to look at the cosine graph, and we're going to try to do what we just did with sine. So big 5 points. Here I've got 1 divided by 1, so I've got 1. So I'm going to put that middle line in again. Ooh, that didn't go very well. So let's put that line in to represent where 1 is, because this graph is going to look pretty similar to that last graph we just did. So let's do this. Good enough. So again, at 0, cosine x is 1, and 1 divided by 1 is 1. So there's my point. Pi over 2, cosine is 0. 1 divided by 0 is not possible, so I have an asymptote. At pi, cosine is -1. 1 divided by -1 is -1. So I need to put a point at -1. So again, this is 1, 0, -1. This is 0. 1 divided by 0 is an asymptote. And then 1 divided by 1 is 1. So again, dot, asymptote, dot, asymptote, dot. And if we follow the same logic that we did before, just before this asymptote, we have positive values really small. Positive, but really small, becomes asymptotal when we reciprocate it. Oh, I don't know if I said either of those words right. Just to the right of the asymptote, we again have really small values, but now they're negative. So 1 divided by a negative is a negative. So we end up with this. And what you should see is it kind of looks a lot like what we did with cosecant. It's just been phase shifted. And you can see that even better in the proper graph from a computer. This is what secant looks like, and this is what it would look like with our kind of sketches. And again, I'll tell you where the asymptotes are, not at y. The asymptotes are, well, the first one's at pi over 2. And after that, they're still exactly pi units apart. So every pi units, every whole distance of pi, we'll find an asymptote. So that's where the asymptotes are. And again, this is what it would look like with pen and paper. Now, I don't know why, but for some reason, this kind of looks like a really sad person all of a sudden. So here, I'll make him happy. Yay! Yay, math! All right. Anyway, so here are the 4 graphs that you need to know. And again, they're a lot less useful in the real world than the sinusoidal functions sine and cosine, but you do need to know what these sketches look like, and so you can either memorize these 4 pictures or you can develop them the way that we developed them in this video. So in the next video, we're going to actually do some transformations to those 4 types of functions and make some sketches of transformed reciprocal and tan graphs. Okay, so I'll see you in that video. Bye.